Welcome everyone, thanks for coming. Always nice to see people here on a first day of tutorial in the morning. I'm Gil Forsyth, this is Phillip Cloud. We're going to be doing this tutorial on Ibis. Just a quick temperature check. Who here has heard of Ibis versus just wandered into the room? Okay, 50-50, sweet. So we'll go over what Ibis is very quickly and then we'll dive in. How many of you work with databases? Just like at work, you got to pull data from something. Yeah. How many of you really love SQL? That's totally fine if you do. That's not a bad question. Yeah. Okay. Good. Totally. Just taking the temperature. That's fine. Great. So we're going to be going off of this repo here. It has a few Jupyter notebooks in it. So if you haven't already, please take this time to go to this website. This is ibis-project/ibis-tutorial. Clone that and create an environment using your tool of choice. We're also happy to circulate and help troubleshoot environment issues, get you set up, or you can create a code space by clicking this blue button and clicking create code space on main. That is also an option if you're having local setup issues. And then I will talk for a few minutes about what Ibis is and what we're going to try to cover, and then we'll just dive into it. Another note is that we're going to do sort of Carpentry's light style on this. So Philip's going to hand out Post-it notes to everybody. You get a single Post-it note, and that's just for when we're doing exercises, like little interactive exercises. I'll ask that when you are finished with that exercise, you put the Post-it note just up on your laptop, just on the outside. It's a quick way for me to visually gauge how many of you are done instead of just asking impossible questions like, is everyone finished? And getting useful information back. So that's what those are for. And then otherwise, feel free to interrupt at any point, raise hands, just shout at me. All these things work. Your style of communication is welcome. And with that, I think we'll kick it off. I promise there are not very many slides. Should put that up for the link. Anyway, Ibis, it's a bird. Otherwise affectionately referred to as bin chickens in Australia. They eat out of dumpsters. That's not what we're about here, unless your data is a dump. We're going to come back to that analogy. I'm Gil Forsyth. I'm assisted today by Phillip Cloud. We both work at Voltron Data. I am one of the Ibis maintainers. Phillip is the lead developer and maintainer. These are places you can find us on the internet. I don't really post much. I just stalk people on Mastodon. Phillip does roughly weekly live streams, usually Ibis related. It's a great channel. Highly recommend it. Also, his name is Phillip Cloud. It's Phillip in the cloud. I mean, that was just kind of meant to happen. Okay, so Ibis, this is a very condensed version of a longer talk, but Ibis is meant to address this, which we all know and love, but there are two main assumptions with the PyData stack and all of these tools, which is that data is local, data are local, and data fits in memory. And that quickly becomes not true sometimes. And so what it ends up looking like when you're dealing with, say, pandas and Postgres, these are just representative examples. I'm not ragging on pandas, I promise. We use pandas a lot. But what it might happen if you're trying to get data out of Postgres or Snowflake or Oracle or whatever, is you're going to connect, you have some credentials, you ask for a table you think exists, it's called ratings. You slurp up the entire table from Postgres into pandas, and then you load it, you parse the types, you perform your analysis, you're just all local at that point. This works great until it completely falls over, right? Because you only have so much RAM on your laptop, there's way too much data there. This has a distinct limit of how much data it can accommodate. Secondly, there's a really good chance that thing on the right, the remote engine, is much bigger than your laptop and much more powerful and also much closer to where your data are stored. So it tends to have a bigger pipe. It can do a lot of things very well. And so one of the things that Ibis tries to do, we'll just skip this and come back, is connect to something like a Postgres remote, ask for that table, just get a schema back, a description of the columns and the data types, build up an expression based on that. You can make certain assumptions like we're adding two numbers together, we're performing a string comparison, we're doing some other things. Generate some validated type check SQL, which sounds crazy to SQL people, and then send it over to the engine, have the engine execute the query, and then only pull back the results of the query. Right? So this means that you still get to do stuff on your laptop, you still get a nice kind of Python data frame API to interact with, but we're not just treating Postgres like a glorified data store, because it can do more than that, as can DuckDB, Snowflake, Postgres. You fill in the icon on the right there. This has a couple of fun things you can do, like it might be actually, depending on what set your local setup or workplace, maybe you're actually connected to a metadata store that can be totally separate from the data execution engine. All you need from the metadata store is a description of tables and columns and data types. Or you don't care about it at all. If you're dealing with a table that never changes in terms of its schema, just define something. Don't worry about reading this, I know it's really small text, but like you define, like, hey, I know I've got 4 columns or 3 columns, I know the types of those columns. You can build up an expression just on the basis of that, and then just go to execute it on the engine when you're ready. Right? So this can make for a nice tight loop for doing some interactive exploration, and it means that, to go back a slide, I could have ordered these better. Ooh. What it can mean is that you can bridge this, what we call the PyData translation problem, which is that very often the tools on your laptop or in dev are different than the tools that are available in a distributed computing environment and or prod. And so you end up doing things like many of us have probably done, like, hey, I wrote this thing in pandas, but now I need to rewrite it as like a Spark RDD because it needs to run on this thing over here. Or you throw something over a wall to a data engineer because they need to redo the data pull because they're actually doing it. All these things happen. Ibis, ideally, lets you reduce this a whole lot, right? Because you can write against like a sample that's local, build up the SQL query, and then that's a SQL query that can be executed against the production database and will run. Right? So we try to stop you from having to rewrite everything all the time. That's sort of one of the main things here. I think that might be all the slides, just out of order. Great. Okay, quick temperature check. How many people have an environment set up and are sort of ready to go-ish?
Almost.
Almost, okay, that's close, that's close. All right, I will go over here and we can, is this big enough for people to see? It's okay in the back there? Great. All right, I'll vamp for 30 seconds and then I'll start. Yes, question? Forgot what I was going to vamp about. How's everyone like in New York?
Maybe I got your link. This is the...
Yes, go to Ibis project, Ibis-tutorial, clone the repository, and there's a command in there for pip and mamba to create your environment. Yes?
That's just a random thought. In our last presentation for Porto, they also used the Palmer Penguins data set. So.
It's a great data set, yes. Yeah. We love the Palmer Penguins. Thank you, Alison Horst and Alison Hill, for publishing it. It's always nice when your sample data sets weren't put together by eugenicist. Yay! That's why you shouldn't use Iris. Just putting that out there. Yes. We won't broadcast it.
È così bello, quanto è grande?
Oh, sorry. We'll get it.
C'è un sacco di feature.
I'm going to get started with this, but I'm going to try to talk slowly, and I'll also go over some general ideas. So if you're waiting for your environment to solve in the background or things to spin up, we should hopefully get to the same place at the same time. So the first thing I'm going to do, and you can do too, is run this first cell. This is going to download the Palmer Penguins database, dataset, and then I'm going to load it into Ibis. So for this tutorial, we're going to be using mostly DuckDB. DuckDB is an analytical database. It's similar to SQLite, whereas SQLite is more of a transactional database. It's designed for putting stuff in. DuckDB is for performing analyses on data you already have. It's also just a single file locally. It makes it very easy to use on your laptop. We like to use it for tutorials and just honestly for general data analysis. It's really good and very fast. So once you have a DuckDB file, like you will if you run that first cell, you can import Ibis, and then we can connect to it. We're only going to be doing analysis on this, so we're just going to treat this as a read-only connection. That note you can ignore because we opened it as a read-only file, and I forgot to update this. And then once you're in here, you have this connection, you can call list tables. And list tables will tell you what are all the tables inside of this database. This particular database only has one table, which is also called penguins. And so then you might want to pull that table out so we can begin to interact with it. Because right now we have our collection of tables, of one table. So you say penguins equals con.table penguins. That means give me the table called penguins. Just so I say penguins a lot, I'm assigning it into a variable called penguins. We'll hit semantic satiation soon, it'll stop making sense, it's fine. And we can see that if I just look at this penguins variable, it says it's a database table, and then it's showing us the column names and the column types. Right? DuckDB is is not a CSV file, so like these columns have proper types that we are reading and parsing, and then saying here's what they're floats, ints, strings. So at this point, this is just a representation of a table. That's all we've grabbed in the database. It's just give me the column names and give me the column types. That's the only communication we've done so far beyond what tables do you have. But you might want to look at the data. So you can call, for instance, head, like you would in pandas, and then we're just going to add on an extra 2 pandas. I'll talk about this in a second. That'll show you those first 5 rows in a data frame. We also speak with PyArrow quite frequently. And so similarly to PyArrow, we'll give you those first 5 rows as a PyArrow table, slightly less well formatted in a Jupyter notebook, but all the same data, and that's the important thing. If you just call head, you'll see that you get this sort of representation of what the operation is going to do. So one of the things about Ibis is that it's a deferred execution model. So as you sort of call methods on the table, we're going to build up this expression, which might be performing mutations, selections, aggregations, group bys, order bys. And then when you're ready to execute it, we'll take all of that, compile it, generate a SQL string or something else, and then execute it. So what you see by default when you do a bunch of methods or just head is that, well, you start with a table and then we said take a limit of that, we're n equals 5. That's what the head is. It's a select star from table limit 5 in SQL speak. And it would get longer and longer. For the purposes of a tutorial, we tend to turn on interactive mode, which means we will execute things eagerly for as much as we have to in order to show you the first 10 rows, just so you get a sense of how the query is coming together. So while most of this tutorial will be interactive, hit go, it runs something, you get an answer back, just know that that is one way of interacting with Ibis, but you can also build this thing up much more selectively without constantly hitting the database. This might matter more, for instance, if you're dealing with Snowflake or BigQuery or something that exists on the internet somewhere and you don't want to consistently be running stuff over pipes. Maybe the latency is a little annoying. So I'm going to turn on Ibis interactive mode as true, and then you'll see that when we call head, it's actually just going to do the head operation. And then we'll render it out for you in a kind of nice table format. But we're only going to execute as much as we need to show you 5 rows. That's sort of the deal here. Or 10 rows, actually, but we call it head, so 5. Okay, so quick primer. We've got tables and we've got columns. In pandas land, this would correspond to like a data frame made up of series. So penguins is a table. It's a collection of one or more columns. Each has a specific data type. So you can look at the table. We just did that. You see that if you look at the type of penguins, you get a bunch of stuff, but you see it's a table. That's the last word is the watchword here. If you look at a single column of that, which we can do by just using an attribute syntax here, you look at just like the species column, you see there's the first 10 rows of it. If you look at the type of that, you'll see that it's a string column. So tables and columns, tables made up of one or more columns. Okay. So the first thing we're going to do is just start interacting with this data set a little bit and just trying to get a sense of different Ibis operations. If anyone's ever used dplyr or dplyr in R, it's a very similar model. So the first thing you might want to do is filter down on the basis of the values in one column. So the way you do that in Ibis is you say filter on the table, and I want to look at only those rows where the species is equal to Adelaide. And we'll just take it as rote that that's correct. I mean, I can't see what all the columns are, but all the rows are. We might want to further add an extra condition to our filter and say we also want to look at only those penguins who are Adelaide species and live on the island called Dream. So we've got a few options. We can either use an ampersand to chain the two filter predicates together, and then you'll see that we get only the Adelaide penguins on Dream now, or you can pass them in as items in a list. That works exactly the same way. That's just what choose your pleasure. And just to show you a little bit of what Ibis is actually doing under the hood, there's always this ibis.showSQL command that you can wrap around any Ibis expression, like this table filter operation. And if you know SQL, this looks probably, roughly speaking, like what you would expect, right? Select all the columns from the table, and then give it a where the island is Dream, the species is Adelaide. So that's actually what's being executed on the DuckDB side. Sometimes the SQL we generate will look much grosser than this, but we try to keep it clean. All right, so that's a filter operation. It's a common way to kind of drill down into your data. Selection, very straightforward. This is just sub-selecting a number of columns. So you've got a few options for how you do this. Again, this is just preference. So you can type out the names of the columns you already know. So species, island, year. You can similarly use the, if you want to use tab completion, you can always use these column objects that are the attributes of the penguins table, like penguins.species. You got the same thing. Or you can mix and match. That just looks weird to me, but you're welcome to do it. Like, this is fine. It'll all work. The obverse of selection is drop, right? So if you want to remove columns from a table, then by default what you're asking for is all the columns that aren't those columns. So you can drop, say, sex and year. You'll get back all the columns except those two. And then again, just for completion, you can use either attribute access here, or you can mix and match. That's sort of your choice. So that's filter, select, drop. That gets you to where we are. Everything up to now, that's all subtractive. We're pruning rows, we're pruning columns. You can also add things. That's where mutate comes in. So mutate lets you add a column, usually as a kind of a combination of existing values, right? So one thing you might do here is add a column that converts the bill length from a measurement in millimeters to centimeters. So that would just be dividing by 10, and we say .mutate. We give the new column name. In this case, bill length cm is equal to something in the other columns in the table that we can then perform some operation against in order to generate the new values. And so you see at the end here, we get bill length cm, which is the number of centimeters in the bill length. So all of these up to now, that's mutate. We'll do a lot of this. All of those are just single methods that we're calling on a table, right? Calling just filter, just select, just drop. But all of these things that we're calling, they're also returning tables. And so what that means is that we can chain methods as we go, right? Because you have a table, you call a method on it, you get a table back, you call a method on it, you get and it just continues this way. And so this lets us build up more complicated queries as we go by chaining these methods together. So in this case, and this is not the most complicated query I've ever written, but we're going to select out 4 columns, and then we can just drop one of them. That's relatively meaningless, but it's just to show you that you can select and then drop, same as you could select and then filter and then mutate and then drop, and mix and match the order. So you'll get just species, island, bill length because we've selected 4 columns and we've dropped year. Okay, so enough of me talking for a second. We'll start with an exercise, and we can also roam and try to get people caught up if you're having environment issues. So we wrote this originally for a European audience, but I still like it. So your PI is a cranky American biologist who thinks the metric system is for suckers. He is wrong. Demands we convert all the existing measurements from millimeters and grams to inches and pounds respectively. We are so sorry about this. And so here are the terrible conversion factors that show you just how preposterous an idea this is. And so the idea is that we want you to take this table, which has measurements of bill length and bill length and flipper length, and depth. Yep, bill length, bill depth, flipper length, and also body mass, and convert those into inches and pounds respectively. And we want to get rid of those pesky metric measurements that make sense and only leave behind the silly ones that we use. Okay, I think we're going to take a look at our solutions now. We suggested 2 different ways of doing this that I might have forgotten to say aloud, but hopefully I wrote down. One is to first mutate, which is create the new 4 new columns and then drop the 4 old columns that you no longer need. So this is how we did this. So you see we're doing the 4 conversions here. I'm not trying to lead you astray. I should have mentioned you can pass in multiple things to mutate. And then we're dropping the 4 columns that we don't want. And then that gives us this, what's called some kind of cursive data set. The other way you can do this, if you so choose, you can use select directly, which lets you select columns both by name. I need to redo this part. And then also create new columns sort of on the fly as you go. And because you're selecting, you're only getting explicitly the columns you're asking for. So while, for instance, bill length millimeter is being used to compute bill length things, we're not asking for it in the selection. So the only things that come out on the other end are those 8 columns that we want. It's a question we got the last time we ran this. Does it matter which one you choose? And the answer is really complicated, but mostly no. So if I show you the SQL for these 2 things, you'll see that there's a difference in how it happens. If you do the mutate and the drop, you're actually going to end up with this subquery in here for the first part. Here's the mutate, right? And then here's the drop, which is selecting out those other ones. If you do the select, you get sort of a cleaner query. This is a simpler query. And this does not matter if you're using any kind of modern SQL execution engine. This will get optimized away and it will make no difference at all. So the difference is really in the legibility of the SQL if you are looking at it, which you may not be. That what I say is that's like the main difference here, I would say. Yes?
With the select in your columns, is name the same? I know here it doesn't make sense, but if you're like overriding the name.
So the question is, if you put a sort of a name collision inadvertently or not into the selection, what happens? I'm pretty sure it might depend on the backend actually. Some backend can support that. I think we'll fail on that. Yes?
Yeah, I'm curious about the SQL that it generates. Is it like the most basic ANSI SQL, or is it like dependent on the client you're connecting to?
Great question. What is the SQL we're generating? And is it just basic like ANSI SQL, or is it sort of, I'll say like dialect specific to the backend? So the SQL that we're generating here is dialect specific. So in the case, because this expression is built on a DuckDB table, this is DuckDB SQL. You can, just for fun, we might have different definitions of fun. here, say like dialect equals BigQuery, as an example. Nope, lied, don't have BigQuery installed. That would work if you have the BigQuery backend, so I don't have it. I've got Snowflake installed. And that's Snowflake, which, and honestly, for this query, there may be no discernible difference there. But yeah, by default, we show you SQL that you could copy and paste into like the interactive SQL thing you got for whatever backend you have, but you can transpile it into other dialects. That's all thanks to SQL Block, which is an amazing project we made heavy use of. Yeah, I've got a lot to say about SQL dialects, but I'm not going to say it because that'll be an hour of me just ranting. Nobody wants that. If you do, lunchtime. Okay, so we saw creating some new columns. We've done select, filter, drop, mutate. So the next thing we're going to take a look at is order by, just ordering your results. So the simplest sort of way to start with is just ordering by a single column. In this case, oh yeah, we didn't save any of that imperial stuff. We're just going to pretend that never happened and go back to using the proper units because I can't like keep up the facade of caring about inches. All right, so if we order by flipper length millimeter, what you'll see is that the flipper length millimeter column is now the ordering column for the table. By default, ordering is ascending. We enforce this. So your backend might have a different default, like when you call order by, maybe it just defaults to doing it in descending order. Whatever it is, we'll make it ascending by default. That's like something Ibis is enforcing on the backend. If you want it to be descending, which is a perfectly valid thing to do, you can do either call desk on it, on that column name, so that's just being like, so the table column name desk, that sorts it where now that column is in descending order, and that's your key for the rest of the thing. Or you can sub-select that because we're not looking at a million columns, you can actually see the results. So note I'm just chaining order by to select just to see the columns I care about. And then here you can see you order by, and you can call ibis.desk around like the string name of the column. This is just another way to do a descending order. These are all equivalent. We select out the options we care about and also descending order. Okay, it's order by. Aggregate. And we're going to start getting into the meatier stuff here. So Ibis has a bunch of aggregate functions. Yes, question?
Before we get to the aggregate,
yes.
And maybe a bit of a silly question, but can you reference any of the columns without specifying the actual string? Is it possible to reference them by reference, say the last column or the first column, etc.?
Yes.
Yes. There's a complicated answer there. We'll get to some of the ways of doing that. There are lots of ways to select things. In the next notebook, we've got some selectors we can show you, which is lots of ways to do this. But also, yeah, in terms of like, show me like the column I was just operating on as the thing. You can refer to that as well. All right. So for aggregates, a straightforward thing you can do with aggregates is just call the aggregate method on the column. So this is just what's the mean of the flipper length. It's going to get back a scalar value, right? That's, we just did the average of every value in that one column, you get that back. If you want to compute multiple aggregates, but just of particular columns, you can do that. It's sort of a weird operation, actually. But if you wanted to group them together, you can get both the mean of the flipper length and the max of the build depth in one command. That's just by passing multiple of these aggregate methods into penguins.ag. So you can show a bunch of stuff in there. This will make more sense in a second. This doesn't make much sense. Aggregates by themselves do this. They really start to kind of make sense when they're paired with group bys, which is when we're going to start grouping rows that have the same value for one or more columns, and then applying those aggregates across those groups. So if you just group by a column and then call ag on it or aggregate, you're just going to get actually the distinct values of that column, right? There's no operation of the aggregate, so it just says, all right, here's what we've got. If you wanted to add a second column to that group by and then call ag, you're going to get the distinct pairings of the values of those columns, right? So here, sort of every species island combination in the data set. We haven't done any other operation on it, we're just looking at what's available in those columns. But then you can kind of take it a step further, which is to say, like, all right, I want to group by species and island, and then call ag on that, and then look at the mean of the bill length. Right? So we're calling group by, 2 columns, ag, mean of bill length. And what that will give us is that those same groupings, right, the species island, with the mean computed for each of those pairs. And then this is really easy to build up into something that's computing a lot more sort of in one go. So if we're grouping by those 2 columns and we now pass in a second operation to the aggregate. So we're doing the mean, now we're doing the mean and also the max of flipper length. And now we're computing both of those things across all the groups we've created in the group by. And then there's nothing to say here that you can't just add more columns to the group by if you need to have kind of more detail or more cardinality in what you're looking at. So if we also wanted to sort of specify sex as one of the things we want to break out, it's adding an extra column here, everything else is the same, and now we've got the breakouts for all of the groupings of species, island, and sex, and then here are the mean of their bill length and the max of their flipper length across each of those groups. This is a relatively, we think, small amount of code to write to kind of, explode out all this information. I don't even know what the SQL for this looks like off the top of my head, what we're generating. Might be fun to look at, but we can do that afterwards. So that's group by, order by, filter, ag, select, mutate, drop. That's sort of like it's like your starting toolkit of like tidyverse verbs is what kind of deep library would call these things. Sort of like the basic tool set. So we've got a few exercises here just to kind of try answering, instead of us just giving you a contrived thing, you start answering questions about this data set. So one is, what's the largest female penguin by body mass on each island in the year 2008? So you can think about how you might, the order in which you might want to do these things. It might not even matter, in fact, I think it doesn't. But being like, all right, well, I need to care about what year in the data I'm looking at. I need to care about what the groups of penguins I'm looking at are and how I want to break out the results. And then same, if you want to look at the largest male penguin by body mass on each island for each year of data collection. Totally unrelated, but I just learned that if you, instead of writing show SQL, you type to SQL, its syntax highlights the output. That's pretty cool. I didn't know that. Sorry to interrupt, please go back to your exercise. Don't let me stop you if you're deep in thought. I'm just going to show our solution to the first exercise, and then I'll give everyone else a few minutes. So here we're filtering by sex and year to get female penguins in the year 2008, and then grouping by island, and then looking for the max of body mass in the aggregate. You could have gone through this a bunch of different ways. The thing you probably want to end up with is a table that looks something like this. Okay, we're going to start to move on here. So for the second exercise, we were looking for largest male penguin by body mass on each island for each year. And so that is accomplished by filtering. The only filtering we're doing is just on the sex of the penguins. And then we're grouping by both island and year to get that sort of exploded view of the sets that have those 2 columns that are individual, and then aggregating over the max of the body mass. So for each year we have data, the breakdown by island. Okay, great. I'm going to run through some quick extras that don't fit anywhere else in this tutorial, but are just useful things to know about, and then take the temperature, and then we can move on to the next one. So casting, this is something that you'll probably have to do at some point, especially if you're dealing with CSVs, which are untyped, and all kinds of things can happen. So if you have a floating point number, you can cast integer or vice versa. And so that's just accomplished in Ibis by calling cast on the column and then giving sort of the string of the type you want to cast to. So int32 in this case takes the float column, turns it into an int. Vice versa, you can cast from an integer, like the year column, to a float. I'm saying this is a terrible idea. Not casting the floats is fine. Casting your year to a float is a terrible idea. Like don't. It's the only integer column in this data set, but that's a bad idea. This is not a number; it's a year. So a much more sane thing maybe to do would be to actually cast the year to a string, so you avoid maybe performing numeric operations on a year you don't need to. But you can cast numbers to strings, and you can cast numeric strings to numbers. So if I first cast a year to a string, I can then cast that back to an int64, and that will work because the string 2007 is easily parsed as an integer. If you try to cast a string that's like ABC123 into a floating point number, that's going to error pretty hard. We can't catch that for you because we're not peeping at the values. We're letting the backend do that. So you're at the mercy of whatever your SQL backend is going to do. But none of them will convert ABC123 into any kind of useful number. Let me assure you, that's never going to go well. However, if you try to cast a, sorry, that's what I did here. Yeah. So trying to cast species into an int32 is going to give you a pretty long traceback. Just telling you that that's not okay. And DuckDB in this case will give you at the bottom of however many lines that was, 140 some odd lines of traceback. It will tell you that it could not convert the string Adelaide into int32, but you're going to have to scroll to see that. Last thing, oh yeah, drop NA drops nulls from a data set. There are a few in this one, so that just does what it says in the box. Cool. All right. Yes. Drop NA, sorry. So if I show you just penguins first, you'll see hopefully that there are a few columns that have like null values, and so though any row that has any values that are null or nan will get removed. And you can be more specific. You can pass in like, I only care about nulls in this column, and we'll only drop those rows then. Okay, so that's what we have here. Thanks again to Allison Horst and Allison Hill for the Penguins data set. It's great. And we'll move on to this second notebook, which is called Mem Tables, Joins, and Selectors. Oh my. Yes, question?
Can I just ask one question about, in the very beginning of that last one, when we pulled in the database?
Yes.
That seemed to take a while,
Mm-hmm.
and I'm wondering what it's doing in the back. Like, it's a 1 megabyte file. It's clearly doing more than just loading it. Is that on the DuckDB side?
No, DuckDB is stupidly fast at this. I think that is probably, so sorry, the question for the video is like, the first cell took a little while to execute, so what's going on? My best guess is conference Wi-Fi.
Isn't that just a local file?
Oh, sorry, this line takes a while?
Yeah.
Are you using the code space or a local environment?
Local environment. I don't know. Maybe.
Happy to troubleshoot that. It's not, it's definitely,
It should
it's on us, if it's on us, if anything, it's not DuckDB. They're quite fast, yeah. That should be very fast.
Like I don't know, maybe it's just my weird environment. I don't know.
If it was the very first time you're importing Ibis, if you just create the environment, it could be creating some, like, doing some bytecode compilation stuff in there, creating those, like PyCache directories. Like, it might just be a one-time startup thing, but generally speaking, that connection call should be quite quick, especially for a local file.
Okay, yeah, I was just wondering if it was doing something to like build indexes or I don't know.
No, especially in this case because the file's actually already been generated by DuckDB, so they've got everything they need in there. So that's
yeah.
Okay,
When
don't
I ran it again, it took 0 seconds.
Okay, that's comforting then. Great. The second time's fast for the recording. Okay, good. Yes, question back there.
Yeah, so given his question, is there some way to control like, the level of logging that Ibis has? Maybe just to check like some kind of those details? If not, it's just a cool idea.
The question is there a way to control level of logging in Ibis? There isn't. We probably could add something like a timings argument or something if you wanted to see sort of what is, I mean, we would be limited to like a given method call and also what information we can get from a particular backend. So like I can say you're connecting to like a cloud database. Most of it's going to be like, we're waiting for something, we haven't got it yet. So, but I agree, yeah, there's more information we can expose
Oh, quick question.
Yes.
I noticed I could put in all the arguments into the egg function itself, like egg this by equals having equals, instead of breaking it out into separate pieces.
Yes.
Do we not like that? Do we like that? Do we not care?
The question is, you can pass in like by and how into ag directly. That's just fine. This is just one way of presenting it. Yeah. Whatever you. Unless we said something is deprecated, then it's an approved way of doing it.
It'd be slightly easier to debug because you can comment stuff out. If there's like a big chain, you can piecemeal comment things out instead of like having one draft of all comment out the arguments. But it's a perfectly fine way to use it.
And just one more question, like, do you support like a categorical data types, like filtering on categorical data types instead of string?
No.
I'm saying like equivalent pandas.
So if the data set has categorical data, Ibis will treat it as a string, but it will still use whatever the database does for like effective, efficient use of categories. So if it's like an arcade file, it's got dictionary encoding, then DuckDB or Snowflake or whatever you're using is almost certainly going to be using that, taking advantage of that encoding. Ibis doesn't encode any of that information in its type system. So you can't, for example, cast a column to that specific representation.
Okay, so let's start on this. So in the first notebook, we just had you download sort of a local database file and then interact with it. That's great if you already have a database file you can download, but there are other ways to interact with data in Ibis. The first of these are mem tables. So for like a table in memory, and there's a couple of ways to create these. So I'm going to import Ibis, also pandas and PyArrow, and I'm going to set interactive mode to true, which again is just for the purpose of this tutorial. You don't have to do that. And I've got a couple of ways that I've encoded some random data here. So here's the first one is a dictionary. And it's the names of some of the Ibis maintainers and how many commits they had at some point, and our aliases when we go on the run. Similarly, I can create a PyArrow table where I'm creating names again of some Ibis maintainers, and then pickle count. We're not quite clear. I think I decided that was the average number of pickles we eat per day. Don't remember. And then a pandas data frame. Again, our names, if we've committed, and then what our first commit hash was. I think I made those up, but they might be correct. So those are that's a Python dictionary, a PyArrow table, and a pandas data frame. And you can create Ibis tables from each of these just by passing them into mem table. So that's the dict, that's the PyArrow table, that's the data frame. You can see T1 is an Ibis table. T2, you can see again Ibis table. I printed the schema of the PyArrow table just to show you that the PyArrow table also has types, and they're string and double, and that gets correctly parsed into Ibis. We call it Flow64, it's the same data type though. So with the dictionary, we're inferring the data types based on what's there. Similarly, pandas also has types. So in the case of object columns, those become strings, the bools become booleans, but also a table in Ibis. Then I just had T2 here for some reason. Don't know. Seems like a line. Okay, so those are mem tables. That's just a quick way to like shove data into Ibis. So especially if you have like a big data frame, you wanted to use it in DuckDB, you can do this. Yes, question?
Does every backend support mem tables?
No, it does not. Wait, maybe? Most of them do.
Not all of them.
Yeah. Some of them, there's all, I think, there's near universal support, especially for small mem tables. Some backends don't have like a good way for us to insert random data into them other than smashing it into a huge string and passing it over a wire. So like if you try to insert, I think like 30,000 rows in a Trino in a mem table, it's gonna take a while. There's better ways, I think, or there's supposed to be better ways to get data into Trino, for instance. That is like a drawback. For things like DuckDB and stuff, they're peeking actually at memory in the Python session and just grabbing it directly from there. So it's zero copy and very fast. Okay, so we have these mem tables we created. T1, I can name these much better, but T1, T2, T3. And now we're going to look at joins. So we did everything previously with one table, now we have 2 tables or 3 tables, and oftentimes data that is interesting or deeply boring are stored in separate tables, and you need to join them together in order to perform some analysis based on values that are in disparate tables. So the sort of straightforward join here is to just do to join T1 to T2 and just pass in a string of the column name you want to join on. So I know T1 and T2 each have a name column. If you join, and you'll get the it's like a left inner join by default. Or inner join. Yeah. And because the name, because the join column has the same name in each table, you can just pass it as a string. If they're different, or if you just want to be explicit, you can also do that and sort of pass in a more explicit predicate here and saying like, I want to join on the T1 column name and the T2 column name. Again, name, yeah. Language design is hard, and okay, but yes. So you can perform the join that way. If you were trying to join across columns that had different names, you would do it in this way and just pass in the appropriate column on either side of that quality. If you have common column names besides the column you're joining on, that'll create a collision. And so Ibis is going to rename those by default for you. So you can see here, we had there's a committed column in T3 and in T1. T1's on the left of this join, right? T1.join. So the committed column in the right gets renamed to committed_right. I think this is the same behavior as pandas, but my pandas knowledge is way out of date. But you can also specify different naming schemes depending on how you want to handle this. So you can pass in the sort of like format string style thing where we're saying join T1 to T3 on name and specify that the left name, if there's a collision, should have _left in it. Oh, sorry. So you see you get committed left and committed right. Right? Committed right is still default there. Or if you wanted to specify our name, you do the same thing. You get right committed instead of committed right. So you can play around with these. This is just sort of if you're going to have like a specific schema at the end of it, you have control over how these names get generated and what happens. Yes, general question.
At what point do you need to switch to using the pandas?
So the question is when you switch from
Or Ibis.
Ibis or DuckDB to pandas. It is up to you. One potential answer is never.
Never?
I mean, this is not just like, it depends on what your workflow is.
Okay,
so everything that you're seeing, yes, it can be a replacement tool for pandas. We're here to play nice with everybody. But so like when you call, like for instance, if I'm not an interactive, you do 2 pandas, that's going to take this join, compile it into SQL, execute it on DuckDB, pull back the results and a cursor, shove it into a data frame. There's your data frame, right? I mean, this is just showing me the first bit of it, but if, sorry, this is showing me all of it. I forgot, I have tables with like 5 rows in them. But that's the entire data frame in pandas of this. Similarly, if I do it to PyArrow, I'll get that entire thing back as a PyArrow table, and we never touched pandas for this, except I lied because one of these tables is actually my data frame, but ignoring that, you wouldn't need it. Yes?
In this scenario, if pandas is the backend, when all this is being compiled, is the result that it generates, is it pandas operations, like, or is it's not SQL? Because I know pandas also can parse some SQL, but I'm wondering if you're...
So the question is, if you're using the pandas backend, which is one of our backends, this will also apply to the Spark backend and the Polars backend, and there's one more, I think, Data Fusion, until like a week ago. Those backends, until a week ago for Data Fusion, didn't accept SQL, or we weren't passing SQL. In that case, it's a DAS backend too. In that case, we're mapping these Ibis expressions, like the thing that like an order by, to some pandas operation, Polars operation. It's more of a straight translation of call the appropriate method on that thing on the data object you have, as opposed to generating a SQL query and sending it over.
And follow up, is it possible to extract that result, like to see what those operations are?
Oh yeah.
Okay.
The question is, can you extract the operations? Debating whether to show you this now or later.
Whatever, it's no
Maybe a little bit later. I do, but yeah, you can see all the operations that are going to be executed and what's going to happen.
Cool.
Okay. But yeah, so you call either two pandas or two pyarrow if you're not in interactive mode. It's up to you what format you want that data in. So you can certainly use this for your initial filter aggregation on some massive thing that's in Snowflake, and then pull back 5,000 rows into pandas and continue as you would from there, or into pyarrow and continue as you would, or you can keep going. I would say, for my part, I mean, like Snowflake is probably faster than your laptop. So like if you can spell everything you want to do in Ibis, it's going to be faster until you get down to what you need, and then you want what you have locally and what you pull back. But if there's something, like we don't support multi-indexes because that's impossible to do in SQL. So like if you really want a multi-index, like you can do some stuff, then pull it into pandas and then add that extra index. It's up to you when you sort of switch from one to the other. We tend to try to stay in SQL land for a long time, not because we like SQL so much, but because the engines are really stupidly fast. Question?
So if you're doing a bunch of things, you haven't actually run anything yet, and then you run it, and then you change something to that last step. Is it rerunning everything?
The question is, you like run like a big command, big expression. It gets executed. You're like, I have to change something. Does it rerun everything? It's gonna be. I think the short answer to that is yes.
Okay.
You can like each of those. Like you have an expression that's like 5 methods chained together. You can, and this comes in the 4th notebook that's not even here. You can call a cache on that, and that'll create for SQL backends create a view of the results up to that point. And then you could then continue from there without repeating the execution. But your sort of the naive behavior is just to execute from start to front, wait, front to back. Right. Start to front sounds like the beginning to beginning.
Yeah, because that's the typical time I would pull stuff into something like pandas, is when like I don't want to do all that work again.
Yeah, so that's when in Ibis 94 standard we just call cache. Yeah. And then from there you can continue on. And you don't need to rename your expression, just like that expression is now cached. So when you go to continue from there, we'll basically retarget what that select statement looks like to pull from the view we just created.
It won't cache again if you call it twice in the same session.
Yeah.
So you can call it once, and then if you run that, you run it a bunch of times, it's always going to be used the cache thing.
And those are temporary views. They survive for the lifespan of the connection, so you're not like polluting your database with like a bunch of randomly named views. I mean, you are briefly, but then they come back.
Just one more.
Yes.
For local databases, you're
Yes.
not paying for compute, right?
Yeah.
Like, but if you're generating this dairy SQL and you're sending it to Snowflake and you're repeating it over and over,
Mm-hmm.
you shoot yourself in the foot pretty quickly because is that something, I mean, anybody has brought up or like in real life usage?
In real life usage, so the question is if we're passing all of the SQL to Snowflake, especially if it's hairy SQL, we're executing it over and over again, are you going to shoot yourself in the foot with costs? It's definitely possible. I don't think that the hairiness of the SQL, in terms of the generated SQL is going to make a difference on that. Snowflake wants to execute that in an optimized fashion also. So like that's going to get optimized down to something that's much cleaner. But yeah, if you were performing like a big query, a bunch, like the cost can definitely go up quickly. We don't have like protections in place for that. Okay, great questions everyone, thank you, appreciate all of you back. So for, where were we? Joins. So default join is a left join, greater join. You can do all of the other joins as long as the backend support them, sending, empty, outer, inner, left, right. And to do that, you can either just specify the kind of join you want as a how keyword. So in this case, this is that, like joining T1 to T3 on name to commit. Those columns actually don't match at all, so the outer join just gives you a bunch of nulls. Superset of those two things. But similarly, and this is just again how you want to use Ibis. You can use like an outer join method instead. So outer join versus join how equals outer does the same thing. This is just what you want it to, how you want to do it. Okay, you can also chain joins. This happens a fair bit. So for instance, you want to join T1 to T2, and then T2, or sorry, then that joined table to T3. Okay. You just call join once, you call join again. This leads to something that I think we'll maybe address one of the questions earlier about referring to previous operations and how you might interact with those things. So if we look at T1 join T3, if we want to filter on the contents of committed write, this column that's been created because of the rename, right? And admittedly, sorry, a filtering operation here is meaningless because they're all true, but let's pretend that there's something there we care about. How do you refer to that column? We renamed it for you because there was a naming collision. But it's not, thank you, right mouse. It's not part of T3 or T1. It's not part of either of those tables. It's part of the joined table that was created. Part of a new table that we haven't given a name to. Right? So if you say like T1.committed write, you're going to get an error because there's no committed write table in T1. If you ask for, well, maybe it's not in T3 either. Like neither of those columns, neither of those tables has that column. It exists in this like ephemeral middle space. One option is you can use a Lambda function. This is totally fine. Just you might not want to write a bunch of Lambda functions. So you can say filter on the results of that join, and then look for some column name committed write equals true. That works. I can prove that it's actually doing something, I think, by saying that to false, and that'll empty out all the results. But writing Lambda functions a bunch can be a little awkward. So Ibis has a deferred operator, which we use the underscore for. If you're an IPython fan, you'll recognize that this might collide with the underscore being the history of your last operation. We're cognizant of this issue, and we're sorry. You can rename it. Trying to find something that's relatively short to type and easy to do. So if this is really going to mess with your flow, we don't want that. You can always import deferred as capital C, or pick your favorite letter. Anything works. Python's very flexible. And what that lets us do is, in the same way that up above we use a Lambda function to refer to like the table that isn't quite a table yet that has that committed write column, you can use an underscore there instead. Say underscore dot committed write equals true. And what that underscore means, effectively, is always everything up to that point in this expression before the method you just called. So everything in this case before filter is underscore. It always refers to everything that's there. And so in this somewhat hairy looking thing, you can see if I join T1 to T3 and I rename has committed to committed write, and then I can do a filter, has committed equals true. So here the underscore is equal to this join and this rename. Here I call a mutate on it, and then I start like doing some divisions on commit percentage. Here this underscore is equal to a join plus a filter. And this last line, the underscore is equal to a join and then a filter and then a mutate. So it's always everything up to that point. So you can always refer to the entirety of the expression you've built up to where you are, and then refer to things that are in there. And you might not always need to use this. It's just we've got to become sort of a very easy shorthand when you're typing. Just be like, everything up to that point, I want to use this. One thing that this comes up with when people get like frustrated with typing column names a lot, and I definitely get, or like table names a lot, is if like you've named your table variable something silly. Like you can refer to the aliases column here in this long way, but you could also, and that totally works, it's fine. But you can also just use the underscore, and the underscore here is everything to the left, which is just the table. Right? So this is always an available shorthand for the table, or the table expression you have. In this case, it does the same thing. Here, the underscore is just the table represented by a long name for a table. Okay.
So basically, the underscore just helps you not typing it again. You just use it. It just refers to anything.
So the question is, the underscore helps you avoid lots of typing and refers to the sort of the thing that is before. Right? Is that right? Yes. So in this case, this is just saving you a bunch of typing. Really, the left click on this mouse tab is like this big. I'm sorry. In this case, it's just the table name. In a case like this, it's referring to that join. So in fact, there's not really a good way to refer to the results of this join in a chained operation. If we broke it up into 2 lines, we could say like join table equals t1.join t3 on name, and then we can say join table dot committed write. That's like a well-known, that's like a column reference that makes sense to us. But if we want to avoid breaking up our expression into a bunch of individual lines, here that underscore is just saying, yeah, this is the contents of that join. So I can just build off of there and keep chaining methods. Answer the question? Okay. So now for some data that I didn't just make up. We've got some IMDb data here. The IMDb data is like a little bit big, so we've subsampled it down to like a 5% sample size, so it shouldn't be too big. You can run these 2 commands to download those files, and then you should see somewhere. Oh yeah, sorry, that's the right thing. And IMDb small, I believe. Then you'll see these 2 Parquet files. So first things first, before we connected to a DuckDB Palmer Penguins thing, we just said connect to palmerpenguins.ddb. That was the existing DuckDB database that we had, like a SQLite database that we downloaded, you connect to it. You can also connect to DuckDB with an in-memory connection, which just says, I want to use DuckDB. There's nothing in there by default, but you can throw stuff in. And that's what we're going to do here. So we're going to start this in-memory connection, and then we've got some Parquet files we want to look at them. So I'm going to read in those 2. So in this case, I'm reading in the first Parquet file I downloaded and just naming I want to call this, I want to give it a table name of IMDb title basics. I'm going to read in this other Parquet file, call it IMDb title ratings. And remember what I was generating here. You can see there's basics, there's ratings, those get loaded in, and you can interact with them like they're any other Ibis table at this point. They happen to be backed by a Parquet file, but once you've done read Parquet, you don't really care anymore. I should say for people who are familiar with, this is a view, so if you delete the Parquet file, then you care. The data's not there anymore.
How do you know the size of the data?
How do you know the size? So in terms of the size and megabytes on disk, there's not I would use DU in Linux for that. But in terms of the row count, you can say, what's it called, basics. Count. So the basics table is 479,000 rows, give or take.
Is there any info equivalent?
What was that?
Info equivalent where I can see how much size it has been occupied in memory?
No, although it doesn't matter as much. Sort of weird. The question is how much space is this going to take up in memory? This isn't really being loaded into memory as the thing. It's sort of a trick that way. So DuckDB is an out-of-core database, so it can. One of the benefits of using something like DuckDB here, and where it would perform admirably versus pandas, is that the limit of the data set you can load in and operate on is limited by your hard drive size, not how much RAM you have, right? Because it's very, very fast, very parallel, and it will drop things into and out of memory for you to make that happen. It's very good at it. So if you've got a 1 terabyte hard drive, you can load a 900 gig data set and start doing operations on it. And that, actually that should work. But yeah, so we don't expose how much, we don't know how much space that's taken up in memory. It's sort of a fluctuating thing. Okay, so we've got this basis column, this ratings column, we've loaded in from Parquet file. So just a quick exercise just to enforce the join thing, which we want to join basics to ratings on the tconst column. That's the join column here that's available to us. So I'll give you guys a few minutes for that, and then we'll keep going. Question?
Yeah, with the like table objects, is it not trivial to do auto completion? Excuse me, with the column names of them?
Yes, it should be available.
Sorry.
Is it non-trivial? Was that the question? Yes, it is non-trivial. It is trivial.
Oh.
It is available. Yes, you can
it's
do that.
available?
Yes.
Oh, I just,
Yeah.
okay, maybe it's not working.
I think one of the things that happens with the column names though is that like the tables also have a bunch of methods on them, and so the column names are in there, but so are all the methods that you can operate on. So if you like know the first letter of the column name, it'll be a lot easier to find it. But like if you're searching for column names in amongst the 40 or 50 table methods, it may not be the fastest way to get there. You can also just look quickly at like what are the column names. Like if you weren't an interactive or you just want to see what they are, it's available as well.
Oh, follow up. Is it non-trivial, we're going with this same premise, to use that for the deferred underscore operator as well?
That is non-trivial. Okay, is it non-trivial to add tab completion to the deferred operator? The answer is yes, it is highly non-trivial to do that. We've thought about this, it would be really great. We don't know how to do that yet. Okay, in the interest of time, which is limited, I'm going to move on and skip a few. Well, I'm not going to skip a few of these exercises, but I'm going to run through them just more as a demo. So I want to have a chance to show you all what we kind of wanted to show you. But these notebooks are available, as you've seen, and please do go through them. There's an entire third notebook which we weren't planning to get to, but if you want to learn more and play around with some PyPI containers data, there's a bunch more, with more pros as well, since it's not meant to be delivered in person. I recognize some of these require a person saying, like, why the hell is this here? So to do this first join, basics.join ratings, and just say tconst, and that's your join. The second exercise I was going to do was to have you join on tconst and then just select out 5 columns here. I just have to run these so I have the thing working. Maybe I've done. So this last exercise is the one I care about, sorry. So we're going to join a table, and then what we want to do is compute the 10 movies with the highest average rating who've received at least 100,000 votes that aren't marked as an adult film. So that's sort of the query we have at hand here. And it's big, but we can step through it, and these are all methods we've looked at. Right? So we are taking the basics table, we're joining it to ratings on tconst. So that's our big join table that now has all of the movie titles and the rating and the number of votes. We're using this helper method called rename, which changes the column names so to be all snake case, because we don't like camel case names in Python land. And then we're filtering on 3 things. One, that the title type is movie, because these also include TV shorts and TV shows and shorts and documentaries and other things. We're setting is adult equal to 0 because this is a family-friendly tutorial. And then we're specifying that the number of votes has to be greater than 100,000 because, just because the movie you made with your friends last week has like a 10.0 on IMDb, it only has the 1 vote, it shouldn't be higher than the Shawshank Redemption. Then we're going to order all of those because obviously we care about the ratings being in descending order by the average rating, but have that be descending. and then we're selecting the title and the average rating. So we should get just a list of movie title and rating. And it should look something like what you would see on the top 10 on IMDb. But this is actually not, because this is a 5% sample, right? We randomly sampled the titles we were looking at. So this is some top movies, but it's not going to be the top 10 because it's only this subsample. However, and this part you shouldn't run because it only works if you're set up for this. But if you have, for instance, Snowflake credentials, to come back to our point about exploiting costs, but which I hopefully do. Good, I do. So I have connected to a Snowflake account here that we've set up. And you can see that it has tables called IMDb title basics and IMDb title ratings. And if you'll recall, when we read in those Parquet files, well, if you recall, there we go. IMDb title basics, IMDb title ratings, same table names, right? If I turn off interactive modes, we can actually look at the expression. I'm going to call unbind, which just means stop treating this like a DuckDB table. I just want it to just be a table, like a generic table object, not bound to any particular backend. And you can see what we really have here is like sort of a recipe that's backend agnostic for how to do what we just did in DuckDB, which is we have two tables. Here's a description of their columns and their types. We're doing an inner join. We're selecting some of those columns, selecting columns from both of these, a bunch of selections. Then we're filtering. Here are the filter predicates. Title type is movie. They aren't adult films. At least 100,000 votes. We're sorting it by average rating in descending order. And then out of that, we're selecting the primary title and the average rating. None of that is DuckDB specific. None of that's specific to anything. It's just an Ibis expression that says, if you have two tables with these names and these columns, perform these operations. So if instead of just saying to pandas or to PyArrow, I call, actually might as well do that. No, just call execute. If I use the Snowflake connection I have, which I've just created, and I call that on that expression, then it'll take a second because it has to call out to Snowflake, and then Snowflake's going to execute that. And this is actually being executed on the full IMDb data set as of the last time we pulled it. So you notice that this looks slightly different. The top film is not Life is Beautiful, it's The Shawshank Redemption. In fact, this, modulo some temporal differences, is probably the top 10 on IMDb. Right? So we built up an expression using a local sample that was only 5%. It was very easy to interact with on our laptops. And then when we were ready to go and fire it off, we didn't need to build up the expression against the full production database. That's unnecessary for our purposes. We had enough to be like, does this look right? We can smell check it. Have I heard of Life is Beautiful? Yes, okay, then this is probably in the right direction. Then you have the expression, then you can execute that thing against the entire production, big, full-size, fill in your, adjective choice here, database. And you're not, so your point about cost explosion, you don't need to necessarily develop against the big, heavy, fast thing that's prod. You can develop against something that's a subsample or a smaller section of it. You can do that locally, depending on you. You have to make, it's your responsibility, or with your database admin or your data engineers, you have tables that match, the column names need to match, the data types need to match. Like, this is the restriction. But beyond that, there's no difference between running this on Snowflake versus BigQuery versus Postgres versus DuckDB versus SQLite versus Trino versus, I can keep naming backends. Like, they're all the same. Question?
Is there any built-in way to say, like, run it on Snowflake and then say, I need to say, I want a local sample cache, and then I can work with that and then eventually switch back to the real thing?
You can do that. What I would do for that is I would say, so what I would do is I would connect to Snowflake, get the table expression, there's no table sample method right yet on, or we just added one? Okay, coming up in the next release, there's a table sample method. Otherwise, if you're okay with a bias sample, you could do like a limit of like 10,000 or something. Dump that into do two PyArrow. You have a PyArrow table, which you can read directly in memory from DuckDB, and then you can start working with it locally, and then you can dump it to Parquet to save it for later. It's a perfectly viable way to go about that. Question?
Is there some kind of extension API, like for example, I don't know, we're running everything on Snowflake and we decided to migrate to some new technology that just showed up.
Yeah.
And you know, I have like the necessity to implement just part of Ibis for that platform, like before you announce like this production release or something. Is there some way for me to implement those kind of methods beforehand? Just partially? Not like in the hacky way, because I think there are many hacky ways to do so.
Yeah, it wouldn't be a hacky, but the question is like, how would you implement this for like a flashy new thing your company is switching to that's not yet available Ibis backend? There is some variable difference in what backends implement. Like each of these, I don't want to delve too deeply into internals right now, but like each of these expressions is decomposed into a series of operations. Those are agnostic to backend. And then what we're doing is we're mapping an operation, like say, take the log of some number to some base B, to what would that be in this SQL dialect. If you don't do the mapping, then when Ibis tries to do it, it just falls over, right? But if you know that you only need the 7 operations that are in your new thing, you can implement a full backend that just has very limited functionality to begin with. Does require, that's like a non-trivial undertaking unless you've been in the internals for a while. But each of these backends in the code base are separate. You can go and look at one of them and see what's involved. I wouldn't say it's going to be easy, but it's very doable, and it would be, if you did it, it would be very extensible from there to then come back in a month and be like, I would like to make this more of a fully fledged backend, not just a trial, and add in all the other operations. Okay, thank everybody for coming. I really appreciate your time.